So today we're going to learn about calorimetry. Right? Calorimetry is dealing with how the energy changes inside of a reaction. So first thing we gotta talk about is what's a calorimeter. This is a calorimeter on the right. Now there's a couple of different things, but what you have is you have this container, right? And what's special about the container is it doesn't let the heat go in or out. So it is self-contained. It's got very good insulation within this container here. In the center of the container, you have the bomb cell. You know, this is a bomb calorimeter. You have non-bomb versions, but this is where your reaction is going to be taking place. Reaction or chemical or whatever. Okay, so you have your chemicals inside here. They're hooked up to wires so you can start the reaction or heat it up using an electric heater, whatever you're doing for this kind of stuff. But you have a sample that's inside of a bunch of water. This is just water here. And you have water because it has a high specific heat, so it's not going to heat up too quickly. And to make sure everything's the same temperature, this is why you have the stir, because you have a thermometer that's reading the sample, the temperature of the water. Temperature of the water is going to match all of the temperature of the cell here. So that's how we can measure the temperature changes. Alright, now for a bomb calorimeter, what's important to think about is that the volume is going to be constant. Alright, the volume is constant because on the top, they don't really have it drawn, but you have all these screws that are nailing it shut, basically. So it doesn't care about any changes in pressure here. Same thing for this guy. This guy will be like sealed shut. There are other types of calorimeter. So you'll be using, well, sort of, a coffee cup calorimeter. Right? It's just a styrofoam cup. And that doesn't have a constant volume, but it does have a pressure constant. So there's different things depending on the situation. It's constant, but you need to think about those, especially for what's coming up next week. So let's do some practice with a calorimeter. So this is the typical question here. A piece of metal weighing that is heated to 100 and put in some water at this temperature. All right? Then they come to equilibrium. So what we have is we have our water here. Our water, we've got 100 milliliters of it, which means we've got 100 grams, right? Because there's 1 gram in a milliliter of water, thereabouts. And this is going to be at 23.7 degrees. Now we're going to take a hot piece of metal and drop it in there. This is going to be 59.047. This is at 100 degrees. And then they're going to reach an equilibrium temperature that we figured out already. And it's going to be 27.8. So what's going to happen is once we put the metal in here, the heat from the metal is going to be traveling into the water. This is the heat. Now, we're not going to lose anything to the environment. So the heat lost by the metal is going to be equal to the heat taken in by the water. So that's what we're going to use to set this up. And that's the big thing with all calorimetry, is that the energy lost by one thing is going to be picked up by a different thing. All right? So we know the Q from the metal, Q lost, is going to be equal to the Q for the water. All right? These two things are going to be equal. Now, to be fair, one's negative and one's positive, but we're going to keep it all positive just because it's easier. All right? So, for the metal, we know how to calculate the Q. the Q is equal to mc delta T, and that's going to equal the same thing for the water. So it's mc delta T. Now, none of these values are the same, so we have to plug them in one by one. So we know the mass of the metal is 59.047 times C is what we're looking for, right? And then we're going to multiply by the change in temperature of the metal. So it started at 100, it dropped down to 27. So the change in temperature is 72.2. Okay, this is going to equal stuff for the water now. We've got 100 grams of water. We've got a specific heat of 4.18 for water every time. And then for the change in temperature, it went from 23 to 27, which is a temperature change of 4.1. Alright, we're doing some math now. C is going to equal 0.402. And that's going to be in joules per gram Celsius. That seems reasonable for a metal. Metal should be in that ballpark. So it looks alright. Now, what might be bothering you is that the delta T here was positive and the delta T here was positive. This one technically should be negative. And technically you're right. If you're going to live and die by the signs, I agree with you. A lot of times they don't really set it up this way. They set it up this way where the Q of the metal is going to be minus, and we're going to add the Q of the water, because this is losing heat, this is gaining heat, this has a negative delta T, right? So that's going to equal 0. All we're doing right away is we're kicking this over to there, because it helps to think about them being equal instead of adding to 0. But it's really the same math. It's not going to save you too many steps. If you're worried, you can go to this way. It'll work on everything as well. Let's do another one. A little bit different, but not too bad. 2.5 samples heated and then placed in a calorimeter containing 65 grams of water. Temperature of the water increases from here to here. The specific heat of zinc is there. What's the initial temperature of the zinc? So, very similar. We've got a bunch of water here. How much water do we have? 65 grams. And then the water started at 20 and it went up to 22.5. The zinc was hot, 2.5 grams of it, at an unknown temperature. And that's what we're looking for. But we know that C is equal to 0.390. Alright, same kind of set. Let's see if you can set it up. Pause the video to set it up. Alright. So to set it up, we're going to have your mc delta T, and that's going to equal your mc delta T for water. For aluminum here, we've got 2.5. We're going to multiply by C, which is 0.390. I'm just going to leave the delta T as a unit here. You know, we'll figure out what the delta T is altogether. M for the water is going to equal 65 times C, which is 4.18, times delta T, which is 2.5. Alright, doing some solving. I know that the delta T for the aluminum is going to be 696.7 degrees Celsius. Awesome, but that's not our answer. We want to know the initial temperature. The initial temperature, we have to add in what the final temperature is, right? Because this is where it ended. This is how much it changed. So putting it together, we're going to get 719 degrees. All right. That's down. Oh, degrees Celsius. Okay, let's do another one. Okay, so for this one, sorry about the change in audio. We had to change microphones here. A 10-gram block of iron is at 200 degrees Celsius and put in a 100 milliliter solution of water. What will the temperature be? Alright, same general idea, but this one's got a twist here. So for our iron is going to be our MC delta T, and that's going to equal our water. Our water is going to equal MC delta T. But we don't know what either delta T is. So for this one, we're going to have to break apart the delta T. So remember, whenever you're doing the delta, what it's asking for is it's talking about, we'll say delta T, the temperature final minus the temperature initial. Alright? That's what it's usually asking for. Now this does get slightly clouded when Mr. Keeney keeps everything positive, but this is what it costs, I suppose. But we'll help you with that in a second here. So if we're thinking about the iron, we've got 10 grams. We know what the specific heat of it is. The specific heat is 0.45. That's from yesterday or the day before. And then what we're going to do is we're going to put this in. The difference between the two temperatures is this one's decreasing, so I'm going to actually flip-flop it to make it positive so that they equal each other. So the change in temperature is going to be 200 minus something. It starts at 200 degrees and it ends at an unknown value, so it travels this much. This is how much the temperature changes. It's not this, because this would be negative, so I flip-flopped them to make it positive. Do you remember when we moved the Q over to the other side? Well, so when we do that, it changes sign. This is where the sign gets changed in there. So now let's look on the right-hand side. So the M of the water is 100. The water we know all about, 4.18, times his change in temperature. Well, this one's going to be getting warmer. So the first number is going to be higher, and then minus 25 degrees. Okay, so this is how we'd set it up. Now these two are opposites because one of them is getting colder, so the initial temperature is higher. One of them is getting warmer, the final temperature is higher. Alright, so we're going to do some math here, a lot of distributing, a lot of math. I'm going to just jump to the end here. So you're going to get a final temperature of 26.9 degrees Celsius. And that seems reasonable because the water is going to warm up from 25. The iron's going to cool down, but you have a lot more water and a lot higher specific heat, so that's why it's going to be a lot closer to the water's temperature than to the iron's temperature. Alright, next one. Calculate the quantity of heat required to melt 4 kilograms of ice and raise the temperature of water formed to 50 degrees. Alright, so this is a little different. So this is combining the previous 2 days' processes, okay? So if we want to do these, what we're going to have to do is we're going to have to combine the specific heat and the latent heat. So the total amount of energy is going to equal, we're going to start with some ice and we're going to melt it. So we're going to have M times H, and then we're going to add to that another Q, which is when you heat it up to 50 degrees. So we're going to have MC delta T. So this guy right here is when the ice melts, and this one right here is heating the water. And we just have to add those together. So you pay for one, then pay for the other. So the M is 4 kilograms, so 4,000, because we'll just use the numbers we're familiar with. H, the H of F is going to be 334, plus M is still 4,000, times 4.18, times delta T. Well, the final temperature is at 50. What's the initial temperature at? Well, whenever you melt, you're going to be at 0 degrees Celsius. So we're going to go up by 50 degrees here. So we multiply those numbers together, add them up, we're going to get 2.1 2.17 times 10 to the 6 joules, or 2170 kilojoules. Either way, it doesn't matter how you write it. Nice. So let's try another one. Here's another one. The refrigerator can convert 400 grams of water at 20 degrees to ice at -10 degrees in 3 hours. Calculate the average rate of extraction from the water in joules per second. All right, so 2 steps. First step is you got to find the energy. Second step is dealing with the time. See if you can figure out how much energy it's going to take. Q is going to equal 3 things now. So we're going to have mc delta T plus mh plus mc delta T. All right, there's 3 things because we have to cool the water. Then we're going to have to freeze the water. Then we're going to have to cool the ice. All right, ice does not have the same numbers as water does. So that's why we have to keep them separated. So now let's plug in some values here. I'm going to factor out the m for all of these because you can, and it's so much nicer that way. So cooling the water, we're going to have 4.18 times delta T. Delta T here is going to be 20. It's only 20 because we're going 20 to 0 for water, and then we're going 0 to -10 for ice. So we got to keep track of these things step by step, one by one. Freezing, we got rid of the m, so all we have left is the h, which is 334, plus m is already outside there, so times the specific heat of ice, which is 2.03, times delta T, which is 10 in this time. Alright, so we're going to put those together. We're going to get 1.75 times 10 to the 5 joules. That's how much energy it is, but it wants the average rate of heat extraction. This is how much energy. Well, all we got to do to figure out the rate is we're going to take our 1.75 times 10 to the 5, and we're going to divide by how long it takes to figure out joules per second. So it's 3 hours. So we're going to have 3 hours, convert it to minutes, convert it to seconds. So that means that every second you're getting 16 joules out of the system. And you could be nice and change it to watts as well. Alright, so there's that one. Alright, last question. Definitely the trickiest, but the most realistic as well. So we got a laboratory, a coffee cup calorimeter. It is a constant pressure calorimeter. It's frequently used to determine the specific heat of a solid or measure the energy of a solution phase reaction. A student heats this many grams of iron to this many, and puts it into a cup containing this many grams of water at that much. The final temperature is here. The heat capacity of the calorimeter was determined to be that. So what this is saying not all the heat is contained within just the water. Some of the heat gets into the calorimeter, which is true. But, you know, this is the worst case scenario. But that's okay. So what we're going to do is we got to keep track of energy in 3 different things. So let's take it one piece at a time. Where's all the energy coming from? The energy is coming from the iron. Ooh, let's use red because it's hot. The energy is coming from the iron. So the iron is going to cool down since it's changing temperature. We're going to have mc delta T. Alright, this is going to equal 2 different things. It's going to heat up the water just like before. So we're going to have mc delta T for the water. And then it's also going to heat up the calorimeter itself, the frame around it, you know, the metal there. Now, we don't have a specific heat for the calorimeter, but we have the heat capacity, which is as a whole, the unit here. So this guy is going to be C times delta T. Right? That's a capital C because it's not specific heat. It's just heat capacity. So that's the difference between them, looking back to earlier notes here. So now that we have this set up, we just have to plug in some things here. So mass of iron is going to be 69.07 times C, that's what we're looking for, times delta T. The delta T is going to be 69.47 because we started here and we went down to there. This is going to equal stuff for the water now. The water, we have a mass of 81.71, and we're going to multiply that by 4.18, and we're going to multiply that by 6 because the water went from 22 to 28. All right, plus one more step here. We know what the heat capacity is. It's 1.82 times the delta T. What's the delta T? Well, the delta T is going to be the same as the water. It's the same as the water because the water is in contact with the calorimeter. You have to start with the calorimeter and the water being the same temperature. Otherwise, it's just going to get out of control complicated. So now that we have all this set up, we only have one unknown. So we're going to figure out what that is. C is equal to 0.43 for this experiment. So that's going to be joules per Kelvin grams. Since I put it in the wrong order. Anyways, so that's how you can do the calorimetry stuff. Right? Have fun with it.